KW Physics. I'm Mr. McConley, and today we're going to talk about refraction. And refraction, if you were defining it to anybody that you wanted to know what the word meant, you would say it's bending of a wave. So you're bending it, or changing direction. And I gave you a perfect example here, where a light wave is coming through air, and when it hits the surface of the water, it bends. This is why, when you go to reach down and grab something out of the water, the object that you go to grab in the water isn't where you think it's going to be, because the light is being bent, so you're getting an optical illusion. So you're seeing it from this perspective. If you're looking from this perspective, you think the object is there, when really the object is here. Okay, so you misjudge. That's refraction. Okay, and refraction is used to your advantage. If your eyes do not focus correctly when you look at something far away, you get a pair of refracting lenses, aka glasses or contacts. They bend the light, so now the light correctly goes in your eye where it needs to go, and you see what you need to see, and you're happy. Well, the guy that did all the work on figuring out how this all comes together is Snell, and basically early 1600. And here's what he did. First of all, he noticed exactly this concept, and he basically he put some variables to this. So I'm going to redraw the picture, and I'm going to make it a similar picture. We'll have the light coming in this way, and then we'll have the light slowing down. We'll say that this is air, and this is lucite. Lucite, by the way, is plastic, pretty hard plastic. So, what he did is he said, okay, if I draw a perpendicular right here, I can measure this angle. This angle right here is called the angle of incidence. This is the angle that the light is incident upon the lucite. And what we're going to call that, angle theta 1. Similarly, if I continue this perpendicular line, by the way, I didn't mention what this perpendicular line is called. This perpendicular line that is perpendicular to the surface is called the normal line. So try to get used to, I'm going to refer to it as the normal line. The normal line means it's a reference point that it's where you make all your measurements from, the normal line. Well, from the normal line you have the angle of incidence, we call it theta 1. And from the normal line, when you get into the new material, you have another angle that's created, and this is called theta 2, and we call this the angle of refraction. Which seems kind of obvious because the light is incident here, and when it gets into the lucite, it's refracted. So we call it the angle of refraction, angle of incidence. And we call them theta 1 and theta 2. But he came up with another part of this that is much more abstract or far removed. You probably haven't heard of it before. He said that air has an index of refraction. And lucite has an index of refraction. And those two indices are not the same. And basically what it turns out is that air has an index of refraction that is equal to 1, and lucite has an index of refraction that is equal to 1.5. Generally speaking, the higher the number goes, it means it's going to slow down or bend the light more, or it's going to bend the wave more. Now these indexes of refraction are given the letter n. N, lowercase. And this one, since it's where you started, we're going to call it n1. And this one, since it's where you ended up, is called n2. So you can say that the n1 is 1, because it's air, and the n2 is 1.5, because it's lucite. And then he tied the whole relationship together, and this is what is called Snell's law. He basically said this. He said, if you take the n1 and you multiply it by the sine of theta 1, the sine of that angle, and then you set it equal to n2 and multiply by the sine of theta 2. So you take this 1.5 and multiply by the sine of theta 2. This relationship will always come out to be an equality. They'll be equal to each other. So sine of this times that will always equal the sine of this times that. That's Snell's law. And what Snell's law allows you to do is it allows you to figure out how light is going to bend if you know what materials, or you can figure out what material it is if you know the angles it bent at. So let's do one quick example of this. Well, before I do an example of that, let me talk a little bit more about how you come up with these n values. I think that's important. I don't want to skip over that. So if you're trying to find out what an n value is, how do you find an index? Question mark. An n value is arrived at by taking the speed of light and dividing it by the speed in that material. So this is the speed of light, which is 3e8 meters per second. That's right, front page of your reference table. If you know, for instance, what the speed is of light in your material, so I know for a fact that in lucite, light travels at 2e8. Okay, so this is the speed in, we'll call it your material, the material you're interested in at least, right? So in your material, it slows down to 2e8. Then all you got to do is divide 3e8 divided by 2e8, and you will get 1.5, which is what I told you the index of lucite is. So that's how they arrive at these indices. Now there's actually in your reference table a whole chart, and it tells you really common ones. So most of them you don't have to calculate. Most of them, if I say, what's the index of flint glass, you can look, oh, flint glass, boom, you look it up. What's the index of diamond? 2.4. Okay, and then you just use it. But this is how they found them, right? And sometimes you do have to use this equation to find an index. So let's do an example of Snell's law. Perfect example would be, what if we had an interface here between the material water and between glass? And I'm going to tell you that this particular glass has an n value of 1.52, and water has an n value of 1.33. Now this information can be gained from your reference table, but I'm trying to speed the process along with it. Now, if this is your normal line right here, and I send a ray of light in at 47 degrees, there's 47 degrees right there. My question is, given this situation, what angle will the light come out at over here? So, let's go through it. Step 1, we write down Snell's law. So we got n1 sine theta 1 equals n2 sine theta 2. What exactly are we trying to solve for? In other words, of what I've given you, let's put some labels to it. So, what's this one right here, everybody? This is n2 because it's where you're going. Notice the direction of the arrow. This one must be n1 because it's where you started. And this one up here, the 47 degrees, is what? Theta 1 or theta 2? Theta 1 because it's where you started again. Alright, great. So what that tells me really is I'm trying to figure out that one. So let me divide the n2 to the other side. I always like to rearrange before I do anything else. Alright, n1. Plug in our numbers. 1.33. Sine of 47 degrees. N2, 1.52. Now, by the way, just a reminder on your calculator wise, you got to be in degrees on your calculator, and most TI calculators default to radians, so make sure you are in degrees before you start this, or you will not get the correct answer. So you do the sine of 47 degrees times 1.33 divided by 1.52, and what does that give you? Don't finish the problem yet. I want to know what this side gives me. Please give me an answer. Got some people calculating. What'd you get?
0.63.
Yeah. I'm gonna, it's 0.63, blah, 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 blah. And you would leave all that on your calculator. Don't round any of that yet. But how do I get it so it's just theta equals? Theta equals. Like, what do I have to do to get rid of the sign?
Sine.
Yeah, arc sine, the sine of -1. So basically I have to take the sine, the arc sine, the sine of -1, sine to the -1, of 0.63, blah, 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 all that stuff on my calculator. And I get 39,
0.7.
okay, 39.7 degrees. So that tells me, I don't want to block anyone's view. That tells me that if I come in at 47 degrees, it's going to bend and it's going to end up being 39.7 degrees, which is our theta 2. Ask yourself, does that make sense? Do you think it will slow down? Because this is showing that instead of going straight, this would have been straight, right? Instead of going straight, we are slowing down. Do you expect that you would slow down because you went to a higher end value? Yes. People are nodding. If you go into a higher end value, you should slow down. So this seems to make sense. And this is how you do Snell's law for today. Physics.